So welcome to today's panel discussion. We will start a bit by describing what we do, and then we will go on to the open problems, some of the open problems in astrophysics that hopefully lead to discussions on what we should work next and how we should solve these problems. Licia is yes, first of all, let's introduce the panel. So our panel is from Wasserman from Cornell University, Tanja Hinderer, who was our colloquial speaker for today from the University of Utrecht, and Duncan Neill from the University of Bath. And then we have the local people in the audience who will come in briefly to tell you a bit about what they do. At least a few of the local people. So Licia, our institute director, is going to talk a little bit about cosmology to get this started.
Okay. Okay. So welcome, everybody. Thank you for being here. It's an honor to have such a esteemed and famous panel with us, and really curious to know what they're going to tell us about. Now, I go first and I talk about cosmology. I've been asked to talk about matter and gravity in extreme condition, and what does extreme means? Let's see, and what are the open problems? So in cosmology, what we've done, we've extrapolated GR that we've tested with precision on basically solar system scales by some 10 to 13th order of magnitude in scale. Whether that is extreme or not, it's up to you to decide. And assume that it doesn't change, it works exactly the same. Remember when we extrapolated Newton to the orbit of Mercury, already wasn't working in terms of description of gravity, and that wasn't that many orders of magnitude. But anyway, and then we observed the baby universe. Here it is. That's a picture of the baby universe. This light is also polarized, and there will be a colloquium in a couple of weeks' time exactly about the importance of the polarization of the light of the early universe. We've mapped the large scale structure of the universe with 40 million galaxies and counting. Here's the image. Each little dot, it's a galaxy. We've even map directly the mass distribution through the effect of gravitational lensing, and that's an image of that. We've mapped the expansion history of the universe. I think you all know that the universe is expanding. This was discovered about 100 years ago with the work of Edwin Hubble, and especially with objects like this, supernovae, as messy as this, but yes, we did map the expansion history of the universe and discover that the universe is not just expanding, but also undergoing an accelerated expansion. And we came up as a result with the standard model of cosmology, the Lambda CDF model, which has got cold dark matter, which we don't know what it is, and something that drives the accelerated expansion of the whole universe. So the standard model works extremely well, has got 6 parameters, describe a lot of observation of the universe. There are parameters describing the composition and the background evolution, parameters describe the perturbations, very well known. Never mind that the universe is weird. The components are weird. We don't know what dark matter is. We even know less about dark energy. And we don't really know what mechanism put those fluctuations there, why they're so uniform, but not exactly uniform. And that's related to the question of what powered the Big Bang. And that's also matter and gravity in extreme condition, because that's when the entire universe was concentrated to a point. So you have quantum mechanics, you have gravity, and we know that these two don't go together, yet we've seen the result in the sky, and we have very high precision measurement of that result. So I leave you with the open questions. What is cold dark matter? Makes up 80% of the mass of the universe at least. What generated the accelerated expansion? Do we understand gravity at these very large scales? do we understand space-time? Do we understand the vacuum? And what generated the initial perturbation, which is related to what powered the Big Bang? And I think that's enough question for one day.
This year, I was passed on the torch from Mark to lead the gravitational wave group from the University of Barcelona. And I thought this was a good opportunity to brainstorm a bit about open questions in matter and gravity, for matter and gravity in extreme conditions. So of course, gravitational waves open the window to a new kind of astronomy. Okay, so the main characteristics is that you have signals of low signal to noise ratio, faint signals, okay, and this is in contrast with the rest of astronomy, which give us high SNR, high signal to noise ratio, and strong signals. The longer you observe, the stronger the signal. So this poses a number of challenges, some of which we're trying to address. But it has been a rewarding experience in the past decade. So 10 years ago, LIGO saw gravitational waves and has been observing black holes ever since. And some neutron stars, 2 neutron star binaries, and a few black hole neutron star binaries. Okay, so we have seen a category of black holes that we didn't know existed, of masses we didn't know were possible for electromagnetic observations. And just now, we have been observing with Gaia some black holes, which you see here in green, that are in the same range as the LIGO observations. And so these observations, these black hole observations, and the few neutron star and neutron star black hole observations have posed a number of questions. Part of the surprising scenario is that they all have low spin. They're consistent with 0 spin, pretty much. So how have these relatively massive black holes formed if they are not spinning? This is a question that we're trying to address. And some of them are in weird locations, like the neutron star black hole mass gap, where we didn't think that we will see any objects, or they are more massive than we think could have formed. And so these are some of the questions that are posed by, by gravitational wave detectors. Okay, so what we already do here in Barcelona is that we do some detector characterizations where we're trying to understand the difference between signals and noise. We do lensing, we do numerical relativity, and a little bit of understanding what is the neutron star structure from these gravitational wave observations. And so we also do population studies, which brings me to Mark's slide.
I thought you were going to do that. Okay, so Ruxandra asked me explicitly to also show some of my work. So I am this little bar here. So I wanted to share a few thoughts on the business of trying to interpret what all these gravitational signals, wave signals actually mean and where they come from. So there's, as you've probably seen, a category of models, different types of scenarios or channels that have been proposed in literature that can make them. And I just lazily grabbed a summary plot from this review paper, a living review by Ilva Mendel and Floor Broekgaarden, who nicely summarize, in this case, the merger rate in models of binary black holes, but they have a similar plot for binary neutron stars and for neutron star black holes in the different types of models, right? So we have, traditionally, we have isolated massive stars evolving through some sort of common envelope or large lobe overflow phase that end up, some fraction of these massive stars end up as 2 black holes that manage to spiral in by gravitational waves. But there's all kinds of other flavors of channels we have seen in literature, including dynamical channels in old and young stellar systems, population 3 stars, or triples and multiples, which are sort of hybrid between stellar evolution and dynamics. And the point of this slide really is to show you can get whatever you want if you pick the correct scenario. And to further illustrate that, I show here a comparison of a single stellar model, single binary stellar model, where parameters are being varied. And it doesn't really matter that you can't read the font. Just take away that there are approximately this number of free parameters. And then if you plot the chirp mass and the M1 or total mass M1 and the mass ratio, again, you can sort of get whatever you want, right? So if you pick a single model, and then Giuliano, who's somewhere here in the room, has developed a population synthesis tool where you can easily change the stellar model. So you can do the exact same binary calculation, but you change the underlying stellar evolution model. And here he plots the rates or the efficiency of neutron star binaries, black hole binaries and black hole neutron star binaries as a function of metallicity for different stellar models, and in color changing the parameters. So again, you can basically get wherever you want. So the somewhat depressing conclusion from this slide, I wanted to sort of controversially here pose is we have absolutely no idea, because whatever you support, you can pick and tune and tweak until you reproduce some of these first order measurements like rates. Now, what's the way forward? We can do a lot of work on the waveform side, which I don't want to get into. I wanted to suggest something slightly different, is that when you do these complicated calculations of finding the rates of binary neutron stars, for example, you're also making predictions for a slew of other observables. And usually we just throw them away. We don't really look at them. But I think the next step is to say, well, on the way from 2 massive stars to 2 black holes, there are 10-ish intermediate steps that we should all be able to observe in surveys of massive stars, right? So here you see some examples of surveys in the LMC and the SMC. So we have a lot of these data. So I think the time is right to start combining all of these model predictions. Clearly, the details of the model predictions for these haven't been achieved as we have for the gravitational waves. Similarly, we have these intermediate states, for example, a black hole with a main sequence companion. We start finding them now. This is a beautiful example in the LMC. A candidate here, another one in an LMC cluster. It's a bit older. Here at the ICC, we have Nadia and Sara Rastello looking at the time domain aspect of things, so common envelope evolution, which are very brief, but very frequent. They should happen. For every binary black hole you make, you should have a bunch of these common envelope phases. You might have transient features like stellar black holes disrupting stars in clusters. If you make gravitational waves in clusters, you should also have accompanied for every binary black hole a bunch of these transient features. And as already nicely shown before by Ruxandra, we are now with Gaia detecting dormant black holes, which are non-accreting black holes with a stellar companion. And my Gaia colleagues here always look at me with big smiles and winky winkies about DR4 when I bring it up. Apparently, we're going to find hundreds of those in the next data release. And their parameters, combined with the gravitational wave signals, will really help us, I think, to further pin down all these uncertain parameters. Yes, and I forgot my own work. So you can also look in globular clusters, like what are the black hole candidates in there by, instead of finding stellar companions, doing it with dynamical models and looking, using a sort of mass to light ratio argument, the stellar and dark remnant content inside of the core. And so the surviving population of black holes in globulars today also tells us something about what happened in the past and how many gravitational waves were produced. So there I stop. Back to you.
Okay, so I just wanted to put one slide up. So beyond LIGO, we have a number of detectors that will target the rest of the gravitational wave sky. We have Licia that is coming up. We have the Einstein telescope. We have pulsar timing arrays that will soon be releasing data. So we should think in perspective of all these observations when we think about gravitational waves. And now I have a few slides about dense matter from our panel, and then it will be time for questions, which, by the way, I would like people to move forward so that I don't have to run all the way to the back of the room with the microphone. It's maybe a selfish request, but yes. So I think these are Tanya's slides.
Okay, yeah, sorry to speak again. So yes, in terms of recent progress, I wanted to mention also some directions more related to how can we use these binary inspirals to test is gravity in these very strong field situations indeed as GR predicts. That can be done with black holes, and then with neutron stars are really the couplings of gravity and matter as predicted, which is what can be done with neutron stars. And that's also a bit related to using these objects to test for new physics, like from dark matter beyond standard model fields and so on. And just to highlight some recent work, so along the lines of black holes, so of course, yeah, we don't want to spend all our effort doing for every proposed modified theory of gravity, what could the signals look like, but it's interesting to consider maybe some broad classes of scenarios and what kinds of smoking gun signatures we might want to look for. So some of the theories that have been proposed say, okay, maybe GR is a low energy limit of a bigger theory. So if you look at the action of GR, it's linear in curvature in the Ricci scalar. But then the next correction in kind of an effective field theory view might be quadratic in curvature. So then we would like to know what are the effects of quadratic in curvature corrections on the gravitational waves. And first we have to understand, yeah, what do they do to black holes themselves? And here we considered a kind of class of theories that have quadratic in curvature corrections of a specific form, coupled even with a dynamical scalar field. So it's already quite involved, but in that case, the black hole can have hair, scalar hair, so the scalar field can extend through the horizon. And yeah, but it turns out the black hole can only have a maximum amount of hair on its horizon, which is also quite interesting. So that constrains some of the parameter space if you believe in the cosmic censorship conjecture. And also then, as Ruxandra was showing, these multiple bands of gravitational waves that we can in the future access with different detectors. So one could really test for these higher curvature corrections because the signal would look quite different in the early in spiral compared to the later in spiral, where these higher curvature effects dominate or at least become important. So oh, I also wanted to, for this. Yeah, so that is kind of one thing. Another topic is then also related to what do these scalar fields and modified gravity do to neutron stars. Of course, as we know, for neutron stars, there's still so much even more unknown than for black holes because of all the matter physics, but just to think a bit ahead, what kinds of degeneracies might we be mindful of and so on. So yeah, we also considered a scalar field coupled with gravity and related to neutron stars, and there the tidal effect of the scalar clouds around the neutron stars also influence the signals, and those scalar tidal effects start at dipolar order already. So then it gets much richer tidal effects than what one might expect. So now I'm done. Okay, and then in terms of open problems, so yeah, basically what we really want to do is also for the next generations of detectors, which are supposed to be the next instruments for the next 50 years. So they will be basically within our lifetime what we will have. So we need to understand, yeah, what physics can we actually measure about neutron stars and what can we safely neglect? And there's still a lot to be done. Well, I'm sure you all have also other ideas about this, but maybe just one thing I also wanted to mention is that it's important to think of all kinds of a coupled feedback loop. For instance, if you excite modes in the star, they might heat up the matter a little bit from tidal heating. A lot of the viscosities depend also on temperature and frequency and so on. So how does that all kind of feed in? Is it important in the in spiral, or can we just omit all of these complications? Well, we already talked about neutron star black hole binaries, so it was a very relevant question in terms of the waveforms that are quite underdeveloped compared to other kinds of binary systems, both from analytical and numerical relativity perspectives. And then also, I mean, if we now think a bit back to the QCD phase diagram, we had the heavy ion collisions and the neutron star physics, but how do we actually really take advantage of all the information and connect it together? What do we learn and so on? So those were my open problems I wanted to mention.
Lies in connecting the neutron star physics to the underlying nuclear physics. And in terms of probing things like the neutron star equation of state, there's been a lot of progress over the last decade. Things like the nicer pulsar measurements that have given us mass radius constraints and are going to give us a lot more in the near future. And gravitational wave detections that have started to constrain neutron star tidal formability. And these things are starting to help us really pin down get meaningful constraints on the equation of state of the neutron star core. So that's sort of the progress that's being made in astrophysics. On the nuclear physics side of the problem, there have been a lot of advances in theory recently. The theoretical Kerr-affected field theory has started to allow calculations up to twice nuclear saturation density, which is a decent way into the neutron star core. And there's been several experiments that are starting to probe parameters that are significant for neutron stars, things like the nuclear symmetry energy, which constrains various properties of nuclear matter. So there has been a lot of recent progress into constraining physics relevant to neutron stars from both the theoretical nuclear side, the experimental nuclear side, and the astrophysical side. If you go to the next slide. But yeah, so there are still many problems to still probe in this case. Things like the exotic nature of the neutron star core remains a mystery. What sort of matter appears? Where does it appear? What are the properties of the neutron star core? Do we get hyperons appearing? Do we get quark matter appearing? This is a particular problem because, as I've named them here, the mass grade problem and the hyperon puzzle are two puzzles about the nature of the neutron star core. If we only look at things like the mass radius diagram down here, you can see that this green curve has a kink here from the transition to quark matter, but it actually has a visible effect on the mass radius curve only below the masses we expect neutron stars to have. So it's very difficult for mass and radius alone to constrain the whether quarks appear in the core. Hyperons similarly have behavior we would expect would have a effect we expect them to have on the mass radius curve, which we don't observe. And the question is, well, what effect do the hyperons actually have? Because they don't appear to be the effect we'd expect them to have. So there's two puzzles to be solved. There's also need, but beyond that, there's a need to look at how we're using our gravitational wave data. We only have 1 or 2 detections of neutron star mergers right now. But in the near future, we're going to have many more with next generation facilities. And the question is, how can we best use the data we're getting out of the many, many observations we expect to have to properly constrain the neutron star core and in the rest of the neutron star. And while there's been a lot of work on what we can measure, there's not necessarily been enough work, I think, on what we can actually do in terms of nuclear physics with the measurements that we can make. And finally, more as a sort of general point, I think it's about time we start really working on connecting the astrophysical and nuclear physics communities to properly sort of combine our constraints and work out how we can consistently work together and form a common language for combining astrophysical and nuclear physics constraints in a way that doesn't leave leave all the constraints in the nuclear physics domain and fail to translate them to neutron stars. Since I was asked to point out what my work is, this figure here is from my works, and it's trying to start to translate what we get from an astrophysical measurement to the nuclear physics parameters that are relevant in particle collider experiments. So yeah.
Okay, so as Ruxandra can tell you, I only work on things I don't know. So both Duncan and Tanja have done a very good job of describing what I will call the high-hanging fruit, which is high density, phase transitions to quark matter. Can we observe consequences? From a theory point of view, I've actually been reading about this. I'm on sabbatical, so I have time to read. It seems there are various approaches, even to the quark matter. There are liquid drop models, LDMs, as people seem to call them, for nucleons, for hyperons. These can be based on effective field theory, sometimes on mean field theory. All of them depend on parameters, okay, like the bag model. There are energy cutoffs in effective field theories, which Duncan just alluded to. And there are massive couplings in both mean field theories and effective field theories. One of my long-term interests has been superfluidity and superconductivity in neutron stars. These have been alluded to by both Tanja and Duncan. I think the condensed matter astrophysics community is quite definite that these exist. There are two different neutron superfluids, one in the core and one in the crust. The one in the crust is more like BCS, you know, standard Cooper pairing that you learn in textbooks. The one in the core is a lot more like superfluid helium-3, but even more complicated. Superconductivity is in the core of the neutron star. These, and that's also a little bit more like BCS. These have important effects on the evolution of spin and on the one of my other interests, which I'll talk about in my seminar next week, is whether neutron stars can precess. They spin, can they wobble? I have proven that they can't, and yet they do. Okay, so there's obviously something lurking there. I wasn't the first to prove this. I was like the fifth, but there, you know, among many neutron star theorists, there's quite a consensus that they can't do what they apparently do. So that's obviously interesting. Lately, and this is actually something neither Duncan nor Tanja have talked about, and I will talk about next week, is low density. So neutron stars are highly magnetic. The strong magnetic fields lead to modifications of hydrostatic balance. This is known by people who do stars, okay, regular stars, although it isn't. So I actually did a literature search a couple of weeks ago and found one paper that did it explicitly. I thought one of my old friends, Ellen Zweibel, would have done this 20 years ago, but she hadn't. What are the problems? I believe the modifications of hydrostatic balance are extreme. They're 100%. And the reason is magnetic stresses can easily be larger than matter stresses, even at relatively high density. So I'll talk about this next week, so you don't have to come. I'm not going to tell you everything. In the crust of a neutron star, we don't have usual MHD, but we have something called by the experts, which I am not, even though I've written a paper on it, electron MHD, which means the currents are carried entirely by electrons. There are no, you don't have to worry about the overall fluid flow. One thing that I've specialized in, I think since I was a starting postdoc in 1980, is Landau quantization. Electron orbits in a magnetic field are quantized. And you might think that's a detail, but I will show you next week that it's actually very important. In particular, at low density, the electrons go from being a three-dimensional gas to a one-dimensional gas. Okay, and that changes, in particular, the pressure at which it changes a lot of things, but it also changes the density at which the pressure goes to zero. So everything like this table that you know about goes to zero at 1 gram per cubic centimeter plus or minus a factor of 10. Because the electrostatic energy in this, you know, can match the Fermi pressure at around that density. But that changes in a strong magnetic field, and it can be much bigger. Okay, well, that's a big change. There are other crustal uncertainties. I won't pretend I know much about them. It's almost certainly not a simple regular lattice of nuclei. That much I will say with some definiteness. The question is whether it's even moderately regular, or is it just sort of chaotic, multiply connected schmear of, you know, of neutrons and nuclear matter. Something I was actually talking to Duncan about yesterday that's really not known is what is the viscosity of the crust, even if it is starting out as a lattice, after it shatters. So after that happens, it flows like plastic. And so you really need to know what the viscosity is. As far as I can tell, nobody knows what the right answer is. Now, I know there are, you know, greater experts than I probably in the room, but I think that's a true statement. Okay. And usually when people, and I would have to say like me, have put in plastic flow, we make something up. Okay. Okay. And then, you know, nuclei, if they exist in the core of a neutron star, probably not spheres. The simplest models are spheres, but they're probably not. Okay, so these are all questions I don't know the answer to. Since both Tanja and Duncan have brought up modes, I do want to mention that one consequence of superfluidity and superconductivity is that in the core of a neutron star, the simple pressure waves, there are twice as many modes. One of them is what people often call a normal fluid mode, where the proton fluid and the neutron fluid move together. The other is what's often called a superfluid mode, which is where they move opposite. Okay, and so one additional question is, are there any implications that we can see, however, you know, maybe through gravitational waves, of this duality? Okay, that's it. That's what I don't know.
Okay, so thank you. Thank you, Ira. And now questions, comments from the audience, particularly from the students, the master students, the PhD students. What burning questions you have about physics that, this panel and perhaps some of the faculty could answer for you? Questions, comments? Or how to go about answering any of the questions that were mentioned or answered this. Yes. Or if you have any questions from the colloquium.
Maybe I can ask the question again. I asked it on behalf of the young members of the audience, but I don't know if that's really true or not. Thank you, Thomas. Not anymore. But I guess, let me try to reformulate it maybe in a more general and broad way, especially for the gravitational wave experts in the audience. Of course, 20 years ago, there were no gravitational waves. You guys started working on the field. 10 years later, there were gravitational waves. Now we are at a point where we have 10 years of observation. The field has changed a lot. No? At the beginning, you were probably, I assume, theorists speculating about your theoretical ideas that eventually were measured and eventually now have been confirmed or denied. No, it's a big change going from a pure theory field to a theory that now is probably driven by observations rather than theory. And my question was, what advice would you give to somebody maybe in a similar situation in a field that only has theory or in a field that is building up observations? What is, how have you addressed this change?
Okay, Ira, do you want to answer? Give some advice? No.
No good. I have no good advice. Skip the advice. Just go to the jokes. Okay. So I figured I had 4 choices of career. Okay. Become an astrophysicist, go to medical school, go to law school, or open a fruit stand in New York City. Okay. And I figured I was pretty young when I finished graduate school. And I will tell the graduate students here, I had a slightly unique graduate school experience. I spoke with my thesis advisor regularly every 6 weeks, whether I needed to or not. Okay, I hope you're not having that experience. So I made up my own thesis. Okay, nobody gave me I did get a thesis topic. I was asked to write the theory case for the Hubble Space Telescope. Okay, so I was a graduate student at Harvard, and they were competing for the Space Telescope Institute, and they were going to have me write it. Good thing they didn't. Okay, but they didn't get it anyway. All right. So I just did my own thing. I made up a kind of audacious theory of galaxy formation, which I would, in the words of one of my advisors, was correct but not true. Okay. And then I was hired to be a postdoc at Cornell, believe it or not, by people who had absolutely no interest in cosmology. So they asked me, I said I worked on Landau quantization. They asked me to work on X-ray astronomy. I did. And I so this couldn't happen now. See, I'm an old guy. I only applied to So after I finished my first postdoc, I only applied to one place for a postdoc. Okay, and I applied to 4 or 5 faculty jobs, and I got one, and I'm still there. Okay, so my only advice is, well, aside from don't try to go to the U.S. now, but my only advice, other than that, is you know, one of my other friends who actually Andy knows very well, Eddie Farhi, who's a famous theoretical physicist. So when we were grad students together, he always said, you know, it's important to remember you're not curing cancer. And I've always stuck with that credo that, you know, I sort of work on science fiction, but with, you know, applications to observations, and it should be fun. Okay. Tanja had a real piece of advice.
Yeah, Tanja worked
very well.
Tanja worked with Edda Flanagan. But before putting Tanja on the spot, I wanted to say that Roberto and Emparan joined us with another visitor of the Institute. So maybe they want to comment something about their work. Also, Roberto has the Catalan experience, so he might relate better to some of you.
I think I would prefer to give word to our distinguished visitor. I mean, we have several this week. We happen to have several distinguished scientists, and some of them you have already met. But then we have also Jorge Zanelli, who's coming from Chile, and he's a very well-known person in the community working on gravity. And I think that well, he's also a person who I think can provide very wise advice to students. So yeah, Jorge, please.
Well,
You can go over that.
okay. Well, I don't have much to say, actually. I don't think I can have any good advice for young people. Well, first of all, I don't know anything about neutron stars or mergers or gravitational waves. I come from the science fiction side of the physics, that I work on black holes in different dimensions, and it's essentially mathematical work. But I think that the only thing that I give, the only advice I give to my students is to follow their own interest and to follow their own ideas, and don't pay attention to the experts. And don't listen to the experts when they tell you that something cannot be done. I have only one experience that maybe I could share with you. I was working with my first graduate student, and we were looking for black holes in higher dimensions. So we had a theory or a scheme for finding solutions of black hole solutions in higher dimensions. And I happened to be visiting Princeton, and I knew that, well, the big Ed Witten, the great Ed Witten, was an expert in gravitation. He had written very interesting papers in gravitation in 2+1 dimensions. So I wanted to ask him what was his opinion about finding black holes in higher dimensions. So I pulled up my courage and I called the institute and talked to the secretary. He said, well, look, I am a visitor at the university and I would like to have an interview with Professor Witten. And she said, just hold on a second. And then somebody picked up the phone. He said, this is Ed, who are you? And I was paralyzed. I had never spoken to Witten before. I have seen him in giving lectures and like that. And he was a hero. It's like talking to, I don't know, Messi or Maradona or someone like that. I mean, he's a great guy. And so when he said, this is Ed, who are you? And I was paralyzed. I wasn't sure I was talking to him. But anyway, so I said, okay, well, my name is Zanelli. I come from Chile. And so he said, well, what do you want? Well, I want to have an interview with you if it's possible. Okay, tell me, what's the problem? What's the question? I was again surprised. I said, well, maybe when we're working on solutions to black hole solutions in higher dimensions. I said, oh, that's not interesting. I was devastated. I didn't know what to say. I mean, I was silent for a minute, and then he said, well, maybe there's one case that it's interesting in 3 dimensions. Oh, I said, well, that's good. So has anybody done it? Yes, he said, I did it. That means that, I mean, the only interesting case was 3 dimensions. He has already finished it. So I didn't know what to say. I said, well, thank you very much. Goodbye. I mean, that's it. So I went home, I went back to Chile, and I didn't tell my students. I was very coward. I didn't want to tell them that all the work we have been doing was absolutely nonsense. It was irrelevant. But in the way, looking at the solutions of black holes in higher dimensions, we found that there was a solution, a black hole solution in 3 dimensions. And Witten hadn't found it. And nobody had seen it before. And I was really scared. I mean, is this a new solution, or we're just fooling ourselves? Well, it turned out it wasn't it was a new solution. Nobody has seen it, not even Witten. And so we published that paper, and it became an interesting paper. It's been cited. But I think that you have to have some distance with the experts. Don't listen to them all the time. I mean, it's good to be informed, but it's not good to just follow the same steps. Usually you find something new when you go out of the steps of the famous people. So that's my only advice for young people.
Just one comment about this solution that Jorge says that he and his colleagues found. It's the one that I regard, and I'm serious about this, as the 3rd most important solution in all of general relativity, certainly for black holes. After the Schwarzschild solution and the Kerr solution, it's what's known as the BTC black hole. I think it's the most important solution. So it's good that he didn't pay attention to Witten. And Witten worked a lot with this black hole later, okay? So.
Thank you. So yeah, so the advice is to not be afraid, right? And follow your own thoughts. Have the courage to ask questions and follow your own thoughts. So we started gravitational waves astronomy in 2001. And I started by attending Kip Thorne's group meetings. And then Tanja and I and Dave Tsang would watch his lectures that my brother recorded on video. And then we'd go to his group meetings. And it was all about neutron star binaries. So we expected that LIGO would run and very soon find neutron star binaries, because we had found them in electromagnetic observations. And of course, it took another 15 years for LIGO to actually find sources. And it found black hole binaries of a mass that nobody expected. And eventually, 1 year later, it found one neutron star binary and then another one. But the primary sources for LIGO were expected to be neutron star binaries. And Andy, who is here, was the first senior person to see the black hole binary. He actually thought it was a test run by his colleagues at the detector. And it was actually the real thing, and it was his first day as detector characterization chair, checking that the detector was working. The detector wasn't on yet. It was before the science run was started. So I think the advice is to, again, to not be afraid to do things, to be in charge. And I can actually pass the microphone to Andy a little bit to talk about the first detection from 10 years ago today.
Well, no, I wanted to ask a question to the panel, actually, but based on that, because something Ira reminded me of was that, we were not planning for high mass black holes, right? We thought there was going to be neutron stars, but we built a really good detector and it managed to get them anyway. And when you talked to Witten, he told you that this solution didn't exist, and it actually did. So I feel like we weren't really ready for what we saw. I mean, luckily numerical relativity had advanced enough, and we had an ability to find the things that we needed to, but you know, it was close, and I felt like we were playing catch up. And I just wanted to ask about, like, of this list of things that, I mean, matter is just so complicated. I I don't usually worry about matter, and this is why, because it seems like there's a huge list of things, and maybe some of them are easy to do but not so likely, and other things are likely but really hard to do, which is probably the magnetic part. It's the same thing with gravity. So maybe going through the panel, could we hear maybe what do you think is the most likely thing that we're going to be able to find, that we'll be able to both you know, actually do the calculation of and maybe be able to find? So you've got, let's say, 3 or 4 years before we find the next neutron star, probably. Let's say not in this one, next one maybe, or maybe we have to wait 15, and then tests, you know, finding something beyond GR. Maybe, I don't know, when's that going to happen, and what are you going to bet on?
So actually, I'm going to ask a question of my the people to my right and anybody else. So I know one thing, and I know there are nuclear physics people here. One thing that seems to be of interest, which I think, Tanja, you alluded to, is whether neutron stars are sort of dressed by axionic dark matter. Okay, and people talk about discovering axionic dark matter in various ways, including tidal effects, and deformability, but also looking for bursts of radiation when the axions interact with the magnetic fields of neutron stars. So I'm wondering if you have any comments to add to what you've already spoken about related to that.
Not directly. I mean, you also now mentioned these extra axion photon couplings that one might probe, but also, yeah, there's also a lot of work looking on clouds around black holes that form through superradiance. They could give off continuous gravitational waves, or if it's in a binary system, then it would also modify the binary gravitational wave signal. So yeah, those are my comments on top of this. But maybe there are also more experts in the audience who want to comment on it.
Comments? Okay. Other questions?
Thank you. I have a different topic I wanted to ask the panel. So recently, we've seen the advent of large language models like ChatGPT and so on. These tools came out of nowhere and started to play a significant role in homework production. We often call it cheating. I've also seen a study claiming that the statistical distribution of words in published research papers has recently changed due to these tools, suggesting that a large fraction of, or significant fraction of the text published as research papers is produced with them. What role do you see these tools playing? So I'm asking, what role do you see these tools playing in the lives of the next generation of scientists? people who are students today, should they could how much do they learn from cheating in homework using these tools? Thank you. Roberto, maybe what you want to know?
I mean, I think that you made an inference that's not right. Maybe people are using ChatGPT for words, I mean, for better writing and not for writing the paper itself. You said that, well, the conclusion that you have a statistical change in the usage of words, that this means that the papers are written by ChatGPT, and I disagree with this. Okay. That's fine, as long as the content is not produced by these tools. What's wrong with that? I mean, imagine that you hire copy editors to help you improve your writing. Does this mean that they are writing the papers? No.
There is one little problem, right? That usually these AI tools tend to copy, not just necessarily generate, depending. And so if you ask them to generate a bit of text, if they copy it from somewhere else and they don't tell you where they copy and you don't cite or refer, then it's plagiarism. So it really depends how it's being used, and it's the responsibility of the authors how it's being used.
So any comments from the younger members of the audience?
Concerning Copilot and coding, I think that, from my experience, it's not possible to copy and paste, and because sometimes it's not even compiling, but it's super great to understand a code. Instead of reading the full documentation, you can start to chat with ChatGPT and you understand how to use a code really quickly. Then it's up to you to explore things and go in more details. And also, if you have an idea and you want to, by scratch, set up something analysis tool, is great. Then maybe it's not the most optimal one, it's not working at the beginning, but it's like writing this boilerplate part, and so that you can focus more on your scientific analysis. So I think it's not cheating, it's a great tool. In the future, people will use it. So I think it's a necessary additional tool to even teach to younger generation, I think.
Also, I want to add from a student perspective, which is a lot of papers are poorly written. Like when we try to read papers, it's like the physics is there and we spend so much time trying to understand it. So when authors, instead of just asking ChatGPT to write something, they write something, put it there and ask it to be improved, papers can be better written. So scientists can also read better papers, which saves time and saves, time to do more research. So I think it's better in that way.
Yeah, that's a very good comment.
Maybe I can add something. So the English will be better, but the structure of the text need not be better. That's much harder to improve. And I don't think that ChatGPT helps you much with structuring the text and the ideas.
Of course. But at least the writing gets better.
That's right. The writing style, but the structure and the explanation of the ideas, the logic of the ideas, I think it's still far from what ChatGPT can do.
Text produced. I often difficult to read text produced by ChatGPT, especially long texts. There is a certain kind of nonsensical element to it that I perceive. So they'll probably get better. There was a time when computers were sitting in large buildings, and people were doing physics by hand, doing calculations by hand. And of that time would ask, should we learn how to code? And now there's almost no research project that doesn't involve some sort of coding.
So I thought I was going to get away with it, but apparently not. So I had to prepare them very big. I had to go to the hospital with my son. That's why, in part, I was late. And I didn't know the context, so I thought I would say something about neutron stars because it's the only system I know in nature where all 4 fundamental interactions are simultaneously important. So for gravity, that's obvious because they are held together by gravity. They're very compact. For the strong interaction is always strong. But even the weak interactions are strong because, you know, normally, for example, neutrinos have very, very, very long mean-free paths. It's like 1,000 light years. But neutron stars are so compact and so dense that neutrinos can actually be trapped inside. So all 4 interactions are important. And I think, in fact, even though a lot of focus is put, and I'm going to put the focus on QCD, I think in the future, electroweak interactions are going to play a more and more important role because I think they are less explored, their role in neutron star physics. Anyway, then going to QCD, yeah, thought I would say something about one of the main open problems in QCD, which is what is the phase diagram. This was already mentioned today. And in that context, I think what is considered one of the most important problems is whether or not the transition from hadronic matter to quark matter, which we know is there, is either a crossover or a phase transition. This problem has been attacked theoretically and experimentally for decades, and it's still an. And we, of course, didn't solve this problem, but we did show that neutron stars could establish this. And the idea is very simple. The point is that in numerical simulations, people have seen that even if you start with a neutron star, which is purely hadronic, in the merger, parts of the fluid get heated up or compressed so much that some fluid element can start over here and get pushed across the line of first order phase transitions if it's there. And if that happens, then the way that you go from one phase to the other, if it's a first order phase transition, is, as in any other first order phase transition, is by nucleating bubbles. In this case, these are bubbles of quark matter inside this metastable hadronic superheated or super compressed phase. And then a very simple calculation shows that this would give rise to gravitational waves, very much like in cosmology, if there's a first order phase transition. And in this case, the frequency would be megahertz. The usual signal at the merger from the neutron stars is in the kilohertz. So this would be a smoking gun for the presence of a first order phase transition because the bubbles will not appear if this is a crossover. Okay, it's distinct of a first order phase transition. So at the moment, there's no detector able to detect this frequency, but people are working, experimentalists are working on trying these detectors for the future. And this is the only astrophysical signal which is based on purely standard model physics that gives a megahertz, something above the kilohertz. So you can go, just very briefly for the future, one of the things that I'm wondering is whether you can also generate these bubbles and this megahertz signal in the inspiral. Precisely because of some of the things that we heard to colloquium and that were mentioned yesterday. Because during the inspiral, the tidal force of one neutron star will deform the other one. The deformation is large enough, you can actually push the fluid across the first order phase transition back and forth, and this could also produce this. So I'd like to talk to you about that tomorrow. Thanks.
Any questions about this?
Yeah, so the question is if you can generate this phase transition during the merger, then why not in a supernova explosion also?
Indeed, you're completely correct. It could also happen in a supernova explosion. I've been thinking about that. I don't have anything very concrete, but that's something very interesting to think about.
In the supernova, you have far lower densities, so the gravitational wave amplitude will be much less.
Yeah, that's one reason why I don't spend so much time thinking about that. But I think from a theoretical point of view, it's
The same would
it's
happen.
very interesting. Yeah.
Now, in order to detect these things, you'd probably want something like a bar detector.
Yes. So people are thinking about bar detectors, superconducting, resonant cavities, even detectors based on quantum physics. That's probably one way to go if you want to detect these kind of frequencies. So I think there's a huge experimental effort and lots of ideas out there. So I'm optimistic about the future, but at the moment, of course, we cannot detect it.
And I'm trying to think of the amplitude. You'd probably want a bar detector, which is orbiting the neutron star binary, probably as close as the moon is to the Earth or closer.
That would be great.
No, but I'm saying that's probably what you'd want to detect these things. What is necessary? Am I?
Sorry, you want to have a detector next to the neutron star?
Well, I think if I want to detect these things, that's what we need.
Let me rephrase it slightly. I would say you want a merger that happens as close to Earth as possible. Okay.
Yeah, let's not wish for mergers too close. There's a sort of limit in LIGO where we don't worry about things when they're too close because we wouldn't survive them to observe them, so we don't worry about it. It's but I am curious about is there a design detector already? Like remember Ray Weiss designed LIGO back 70s or whatever, and everything was laid out and knew exactly basically what it was going to be to within an order of a factor of 2 in magnitude. Is there something like that designed for this? Still,
I don't think so, because the game is a bit different here. So these are not interferometers. So that has one advantage, which is that they are much smaller and much cheaper. But because they are based on resonance, they're not as broad in their sensitivity. And this is just one example of a signal above the kilohertz. But if you go above the kilohertz, then there's a huge unknown. And I think that's one reason why people are targeting megahertz and gigahertz. So yeah, I don't think, I think people are just trying to, in fact, let me just mention, there was a synergy grant awarded recently precisely to build a network of detectors for ultra-high frequency gravitational waves in Europe. So I think there are lots of efforts in many different directions. I'm not an expert. As much as I can say. Yeah.
I mean, the real benefit of an interferometer is you can scale it up when you need more
Right.
sensitivity. And
sorry, I forgot to say one thing, which is that this megahertz signal has produces a secondary signal in what's known as memory, which could be in the kilohertz. So this could potentially be seen by LIGO or third generation detectors in the kilohertz.
right. But my actual question was also going to be, and this is made for the panel as well. If we got transitions to quark matter right before the neutron star basically merges and then everything goes flying off, is there any signature in the kilonova or the transition back to normal matter that would show up due to the fact that you've got quark matter floating around rather than neutrons?
I would say in the electromagnetic part of the signal, this would be very, very difficult to see, because the kilonova is not transparent to what's coming from the nucleus. So from the core of the star. The advantage of the gravitational waves is that they will just go fly by.
Yeah, all of the matter that comes off the neutron star and that's used in the kilonova comes from the outermost layers where you wouldn't have quark matter.
I really don't know. I imagine what is there must be latent heat that's released. I mean, that's the only thing I can imagine, right? That you get a little bit of heating, but it's probably rather small.
Yeah.
Right?
Let me say one thing. I've been a little quick in the answer. So people doing these simulations do know that if there is a transition to quark matter, there's an observable effect, which is that typically the collapse to form a black hole after the merger is faster. This is called prompt collapse. And the reason for this is that the equation of state of quark matter is softer than hadronic matter. So if you form regions with quark matter, you collapse faster. But this cannot distinguish between a crossover and a first to the phase transition, because the equation of state The only thing that distinguishes is whether you go through the transition smoothly by nucleating bubbles. That's what tells apart the crossover from the first to the phase transition.
Second order.
No, no.
expression.
I mean,
You mean
a rapid crossover, just like
drip, right? You're dripping out.
what I mean is literally what happens in QCD
Yeah.
at zero chemical potential along the temperature axis is just a
okay.
crossover.
Oh, okay.
Yeah. I think
Okay.
there's a question over there.
So you talk about gravitational waves in the gigahertz range. So we're talking about a wavelength this big.
That's fine.
Sounds awfully short.
What's wrong with that? It's better. It's a tabletop experiment.
Yes. These are quadrupole waves as well. I would imagine probably the only way to infer the existence of such gravitational waves would be through some effects locally in the star. Something would change because gravitational waves exist or are being emitted. I don't imagine an awful lot of energy being in this, so you couldn't. I don't know.
Oh, I guess.
I think in these resonance detectors, people think that they will work for gigahertz just as much as for megahertz.
Okay, so let's move on since we are getting to the close. Since we're getting close to the end of the time, I would like to, well, not the end of time yet, not the end of. Yes, we can talk about the end of time. Yes, but I would like to ask the panel what they think would be the next big discovery, if they could predict it, and also if they were a graduate student today, what would they work on? No.
Well, I think if there is a big discovery, it has to be something unexpected. So it's very hard to predict by definition. So if there's, I don't think that we can predict any big discovery. We can predict small discoveries, improvements, perhaps.
Okay, so what would be the next important small discovery that
You
can
should
predict?
ask the experts.
I think that both the Higgs and gravitational waves were expected. Would you call them small discoveries?
I would call them a confirmation, not a discovery.
I mean, I only passed my PhD 2 years ago, so if I was a grad student now, I'd probably work on the exact same thing I'm working on now. But really, I think there's a lot of work that can be done to prepare for next generation gravitational facilities, particularly in the field of astroseismology, which is, I mean, what I'm at least adjacent to. So, yeah, I think there's a lot of work preparing for the next generation gravitational wave detectors and what they will actually tell us about neutron star physics. I think that's a big area that's going to be needed soon.
Okay. Oops, sorry. The other question I had. Question from the audience.
If I was a graduate student again, I'd probably gamble on the large language models in the same way as if I was a graduate student a few decades ago, I'd gamble on computers. Because I think the field is likely to grow. We've seen it grow. It will not stop. So a field that will have more students for me as I grow up and more, maybe. That's what I would do.
Okay, any comments from the students?
Thank you. Well, this colloquium is connecting both cosmology and astrophysics. So I'm interested also on what are the the piece of information that you can extract from the astrophysical discoveries, sorry, that can give you also a clue to study cosmology or the other way around. Right.
Okay, so the question is, what astrophysics discoveries would lead you to learn more about cosmology?
Well, I can tell you what people I think are looking to for the future: cosmic microwave background, polarimetry is a gigantic field, and that can give you a view of potentially of inflation, because there are modes. They're called B modes that largely come from, the origin that's most obvious for them is in the early universe, and the scale of what you should see would measure the energy scale of inflation. So that's a big one. Something else in cosmic microwave background. So I'm sitting looking at a real expert here. I have worked in cosmology, so I can say some other things. So I think looking for non-Gaussianity, the models that people use, there is a minimum non-Gaussianity that has been predicted a long time ago, that comes from basically interaction of the waves with themselves, if you want to think about it that way, in the early universe, or the quantum fluctuations. And if we don't see those, so they were predicted actually by a string theorist, Juan Maldacena, who's at the Institute for Advanced Study. And if we don't see those, I think it'll require a paradigm shift in early universe cosmology. There are people who are interested in implications of string theory for the early expansion of the universe. Maybe the only place where you can see anything observational about string theory would be in the cosmic microwave background. Probably very, very small effects. Okay. And then there are things that are a little, they're exotic but lower energy, like what are the masses of neutrinos, that cosmology will tell us. Okay, so yeah, that's my list.
So since you mentioned astrophysics, let me just mention one little thing. So somehow when we try to infer things about fundamental physics and the universe, we have to deal with astrophysics because the object we observe are astrophysical objects. And as you know, there is a 6 sigma tension out there of one of the parameters of the standard model of cosmology, which rely on modeling and understanding the astrophysics of stars and the stellar evolution and the astrophysics of supernova and so on and so forth. And there we have, 2 things on our balance. Do we throw away the model and we'll believe the astrophysics because the model, it's a bit ad hoc and we really don't know what the components are? Or we throw away the astrophysics and we just say, we don't understand these objects, and then we keep the model, but maybe there was something there and we threw away the baby with the bathwater. That's one thing that couple astrophysics with cosmology.
So I'm just going to add to that one comment, and please don't take it as a joke. If there's somebody in the audience who can tell me why the tip of the red giant branch is a standard candle, please come up and tell me. So I will tell you, I am Cornell's expert on stars now, even though I've never written a single paper on stars. And when I teach stars, Ruxandra, you didn't take it from me. You probably took it from Ed Salpeter or somebody who really knew. But I spent 2 weeks working on that problem, trying to figure out why the heck should that be a standard candle. And if you look in the books, they say, oh, it's because all of the cores have the same mass. And I said, okay, why is that? But it's a phenomenological fact, as good as standard candle as any of the other standard candles, which means not perfect.
Okay, so time is up. But after this, the students have a meeting with the I would like to recommend that you go to these meetings. Unlike this panel, will not be recorded, so you can to the speaker and ask any questions you want more freely. And I would like to say that these are the meetings that as a student impacted my career the most. So I met a lot of people who are later on panels and help they know who you are. So don't do this sort of meetings if there's any advice I can give you.